In this video lab report, I will be discussing and analyzing the constant velocity motion of a racquetball rolling across a court when the net force acting on the ball is 0. The purpose of this lab is to track a real-world observation of the racquetball's motion, then predict the same motion using Newton's second law in a computer model, and finally, see how closely the real-world data follows the principles of Newton's second law. Newton's second law is an equation that allows us to predict the future velocity of an object, in this case, our racquetball. The law states that the final velocity of the racquetball is equal to its initial velocity plus the net forces acting on the racquetball divided by its mass times the time interval we're interested in. In the case of the racquetball, we're interested in constant velocity motion. In other words, the final velocity and the initial velocity are the same. Since we know the racquetball has mass and we're looking at a time interval greater than 0, this means our term F net must be equal to 0. Saying that the net force equals 0 does not mean that no forces are acting on the racquetball. In fact, it tells us absolutely nothing about the individual forces. What it does tell us is that all the forces balance each other so that when added together, the net force is equal to 0. We can use another equation to predict the future position of our racquetball. Final position is equal to initial position plus our constant velocity times the same time interval. Now let's look at the video of the racquetball rolling to see if Newton's second law holds true in this observation. Using a program called Tracker, I marked the position of the racquetball as rolled. I calibrated the system with the ruler placed behind the racquetball. I chose a time interval after the ball was fully accelerated so that it would be moving at a constant velocity. I also made this time interval relatively short to minimize the change in velocity caused by forces difficult to control in the real world, including friction from the court and air resistance. The results of the racquetball's motion are displayed in the table and graph on the right side of the screen. As you can see, the racquetball's motion appears to be linear, which suggests the ball moves the same distance between each frame. The racquetball appears to be moving at a constant velocity motion. It is important to remember that when an object moves at a constant velocity, it must move at a constant speed and direction. To ensure this is true for the racquetball, I aligned the motion with the positive x-axis. If I decided to flip the axis, you can see that the ball's velocity is exactly the same. The only difference is that the position measurements are now negative. To see if this data really does correlate to constant velocity motion predicted by Newton's second law, we need to compare our observed data of the racquetball with a computer program predicting the motion of the ball. We can model this motion by modifying code in VPython. First, we need to tell the program the mass of our racquetball, which we know to be 0.0427 kilograms. We get information for the initial position of our racquetball from the first line of the data table in Tracker, and we can put that information into the code right here. Information about the initial velocity of the racquetball comes from the first 2 lines of the data table in Tracker. Using the information from these data points, we can solve for the initial velocity using the formula change in position over change in time, and our result is 0.914 meters per second in the positive x direction. We put that into the code here. We also need to make sure that the program uses the same initial time and final time that we used for our video analysis, and that the delta t is again relatively small. Finally, we need to tell the program to use all of this information in the equation of Newton's second law. We plug in our 2 forms of Newton's second law into the code here. And again, we're interested in constant velocity motion, which means the net force on our racquetball is 0. We tell the program that here. Now watch the program's prediction of the ball's motion. Already, it looks similar to our video observation of the racquetball rolling. To compare this computer model to the data from our real-world analysis of the racquetball, we can plot the data points on the same graph. As you can see, the model is a pretty good prediction of the racquetball's observed motion. This suggests that the video from our real-world analysis does abide by the principles of Newton's second law. As you can see, the model doesn't predict the motion as well near the end of the time interval. The experiment's line drops below the perfectly linear line from the model. This is most likely due to the slight impact of forces like air resistance that would have decreased the velocity of the racquetball a little by the end of the time interval. Despite slight errors, this flab shows one great example of how Newton's second law can be observed in the real world. When the net force acting on an object is zero, the object follows Newton's second law and demonstrates, as our racquetball did, constant velocity motion.